Hello. In this research, we'll be covering reinforcement learning. Reinforcement learning is a machine learning technique that helps train software to make optimal decisions in complex situations. This is very similar to how human cognition functions. Given the right data, tools, and steps, humans are able to solve complex problems in different environments. On their own, computers don't have the capability to solve these problems, but with reinforcement learning, they have the potential to do so. In this framework shown here, the agent is able to execute an action based on a policy and a reinforcement learning algorithm. As a result, the observation values are taken into account after executing in the environment and after taking into account the rewards. This research will cover the pusher problem, which involves a robotic arm, which is our agent, learning how to push a cylinder into a target. On its own, it is not able to do so because the robotic arm is very lost, so it just randomly moves around in its action space. However, with reinforcement learning and this basic framework, we are able to do so and help it to learn. What we need to know is that there are 7 points of movement along the robotic arm, noted by their hinges, and these hinges are controlled by 23 values that keep updating each time. And as you can see here in the state transition diagram, the transition between each state is noted by each observational value being updated and connected by the amount of actions taken each time. Along with that, we also need to take into account the reward system. The reward system here is modeled by the Bellman equation, and that basically combines the state and action values being inputted with a discount rate and a rewards function, and the maximum is taken out of that in order to get a reward value. Each time that this function is executed, the values of its current position are put into this equation and outputted in order to get a definitive value for rewards. And this helps to guide the agent on its path of learning. However, in this instance, we will not be focusing on one policy, but rather 3 policies, and to compare how well they are able to help the agent solve this problem. The first algorithm we are going to cover is the twin-delayed deep deterministic policy gradient, also known as TD3. Essentially, by having 2 neural networks known as an actor and a critic network, the values are inputted, evaluated, and outputted each time in a deterministic way. This helps to reduce overestimation bias and to keep estimating in a very proper and minimum way in order to eventually get to that target space. This is a deterministic policy, so it is able to keep updating a function each time and focus on one specific movement or movement value. In the second neural network, we have the proximal policy optimization, known as PPO. PPO is a little different from TD3 in the sense that it's more on policy and strict to an entire neural network compared to the one exploration of value from TD3. However, it does have the same actor-critic network being implemented by TD3, and the one very beneficial part about PPO is that it helps to reduce large updates in the policy each time the computer has to keep updating after each time step. This is very important as many algorithms often take large amounts of time to keep updating the agent, and as a result, the agent is able to execute the function at a very time-consuming rate. However, PPO executes in very small increments, allowing the agent to keep up at a constant pace and not fall behind. The third and final algorithm that we're covering is the soft actor critic, also known as SAC. SAC is very similar to TD3 PPO in the sense that it has the actor and critic network. However, it is more probability based as it's a stochastic process, and also has a high entropy, known for its randomness. Essentially, what's happening is that there is more exploratory values being inputted into this neural networks, and each time that the computer agent is iterating in a certain amount of time steps, it keeps exploring and updating its values each time it goes through SAC. So now that we have a general understanding of these three policies, we're now going to observe the results after execution. Essentially, as you can see here, the mean reward for PPO is negative 34.29. The mean reward for TD3 is negative 31.91, and for SAC it is negative 26.51. Also, TD3 has a higher deviation compared to PPO and SAC has the lowest deviation. This is highly attributable to the fact that SAC is more entropy and probability based, so it has the ability to make more random actions and eventually line up with the target cylinder that it needs to push. For PPO and TD3, the possible explanation about why its rewards are much less than SAC is that it was able to get to the cylinder, but due to its restrictive natures in the sense that it's either focused on one value or focused on its own policy, it wasn't able to do much exploring and actually push it correctly into the target space. Of course, this can be addressed by increasing the amount of iterations and time steps. Currently, we have trained the computer agent in these three policies using 100,000 time steps, but we have the possibility of training for over 1 million time steps, which can dramatically increase the learning rate and amount of learning for this computer agent. In addition to SAC's success in solving the problem, we can also enhance it using hindsight experience replay. What this is that it is a method wrapper in goal setting, in helping the computer agent goal set and focus on different types of rewards each time it iterates. Of course, we can also improve the performance of SAC and other algorithms in solving the problem using more objects, tighter spaces, and increased number of joins for the robotic arm. Nonetheless, our findings here are able to show how reinforcement learning can help computers solve more complex issues. Regardless of how well it can function, it is still able to show that it is possible to help computer agents learn in the same way that we humans do. Thank you.